Good afternoon, everyone. Welcome to this anticipatory briefing. Thank you for being with us. Thank you for those watching online. Thank you for proving once again that, we have this tendency to always sit in the back of the room and never in the front. Thank you for all of those who came here. I think it gives you an idea of how many people have been traumatized by their years at school. It's always so hard to overcome. So anticipatory briefings, they are an interactive series of academic-led sessions where we basically bring topics from the GESDA Breakthrough Radar to life, and we ask scientists to tell us their outlook on them for the next 5, 10, and 15 years. It's going to be 15 minutes of presentation, 15 minutes of Q&A. I think we start a little bit late. Apologies for people watching online, but we will still keep the session going for 30 minutes. Our next speaker is a professor of quantum information, computing and logic at the University of Helsinki, where she flew from a few days ago. She's also the CEO of Algorithmic, which is a company developing advanced algorithms to solve complex problems in life sciences. She's also our own GESDA chair of the Anticipatory Quantum Computing Committee. And in this anticipatory briefing, she will share with us how quantum science is revolutionizing our understanding of the physical world, expanding the boundaries of what's possible in technology and computation, and how this is going to impact us in the next 5, 10, and 25 years. Please help me welcome Sabrina Maniscalco.
Thank you. Thank you. It's wonderful to be here, very exciting. I was born with one blue eye and one black eye in a beautiful island in the center of the Mediterranean Sea, Sicily. And as I grew up, the color of my eyes became more and more similar. Now you wouldn't notice the difference. But I kept a passion for opposites, for everything which is really different. And this is reflected also in my work life and in the places where I lived. I did my PhD in Palermo, in Sicily. Then I moved to South Africa and then to Finland. So oscillating from the really northern south of the world somehow. And this is just an image to tell you I really like opposites. I thrive in the middle of opposites, from the snow and the cold of Finnish weather to the beautiful Mediterranean Sea. But the reason why I'm talking to you about opposites is because this also, I suspect, has a lot to do with my choice of working and researching in quantum physics. During this talk, I will go back and forth talking about different opposites, but one of those will be about quantum and AI. These are two very different exponential technologies, and I will argue that combined together, they have the power to unlock really disruptive potential for many, many, many applications in our society. But I'm a quantum physicist, so I will start with quantum mechanics, and these are the words of Nobel laureate Anthony Leggett. He says that quantum mechanics is very much more than just a theory. It's a completely new way of looking at the world, involving a change in paradigm, perhaps more radical than any other in the history of human thought. So I want you to think precisely this, a change in paradigm more radical than any other. And this also has to do with quantum computers, because I will briefly talk about quantum computers, and quantum computers are just different. They are not faster. They are not more powerful. They use a different logic. They are programmed using algorithms that have a completely different way of functioning. If we think in terms of quantum physics, which is at the basis of quantum computers, we have the theory right. We have a mathematical language which is very beautiful, and I like it very much, but it's a language I don't share with you. So very often, when we think in terms and we try to explain about this fascinating phenomena, we have to use metaphors. And quantum physics is also fascinating because it is counterintuitive. We have the mathematical language, but we cannot picture this phenomena. And this leads me naturally to explain the basic of computing and of quantum computing. So computers work by processing and manipulating information. through algorithms. And the fundamental unit of information is the bit, and the bit represents two opposite values, 0 and 1, or up and down, or transistor on and off, opposites. But the quantum version of the bit, the qubit, is different. You see here, in this image, a representation of a superposition. You see this sign plus of the two opposites, 0 and 1. And the quantum bits can be in 0 and 1 at the same time, in a way. And this C0 and C1, these two letters, they represent complex numbers that are really can take any value. So an infinite possibility arises from them. So you see how quantum mechanics goes from opposite to many possibilities at once. And quantum computers work exploiting phenomena like quantum superposition and entanglement. Entanglement is a very spatial correlation between different particles, could be atoms or electrons, that is very different with respect to what we experience in our daily life. In our daily life, we are not used to quantum physics. We are used to what we call the classical physics that follows different rules. That's why it's so counterintuitive for us. Now, let me tell you some facts about quantum computers. The first one is that they are already available. You can use them via the cloud. They are also available on premises in certain places around the world. And already now, they are able to simulate, or they can be used, and they can even be competitive with respect to certain brute force, really classical techniques and methods. Okay, so they are useful. They are not yet commercially useful, but they are useful to advance research, and they are doing it already now. Something that is happening, and it's very really important nowadays, is the integration of quantum computers with supercomputers or high-performance computers. Because I said before that these are two different modalities of computing. They don't exclude each other, but they can be combined. And this integration is going on already now. And then in the end, I will say that some estimates, McKinsey estimates that quantum computing global market will reach 50 billions in 2035, but the core quantum applications are expected to unlock more than 1 trillion, 1 to 2 trillions in economic value in the future. So a bit more about quantum and AI, in which sense they are different. I will refer to this with a specific example, an example of chemistry, so simulating molecules. And very often, if you think about a drug discovery pipeline, we know that machine learning needs to have training data sets, and very often the answer is as good as the data that we input in the training data sets. And so if you think in terms of simulating molecules that can be very far from the bio-like molecules that exist today, there can be problems by using machine learning alone. And we also know that because they function as black box, there can be difficulties with the interpretability, so the explainability of the results. And also, in certain applications of machine learning, we know that the cost and energy consumptions and therefore sustainability are an issue. On the other hand, quantum physics and quantum computers are naturally able to simulate molecules because molecules are quantum objects. And they do so ab initio, so from first principles. They do not need the training data sets. And therefore, you can imagine to complement with AI. They are, of course, an early stage technology. They are prone to errors. Quantum computers are still noisy. And therefore, they are clearly improving, but the size of the complexity of the simulation is something which is expanding gradually to reach commercial and industrial value. And this is an example of how you can imagine the integration of quantum and AI. You can imagine to simulate on quantum computers new molecules ab initio from first principles and use this data as training data for AI. In this way, exploring the vast and largely unexplored chemical compound space. Now, summarizing this part of the presentation, my opinion, and not only mine, is that these two exponential technology will be combined together in the future to lead to what is the ultimate exponential technology. And now I go to the anticipatory briefing that I chaired. Many contributors that are esteemed physicists from both industry and academia contributed to this document. And this document is aimed really at telling you what we think might be the future in 5, 10, and 25 years, which is difficult, obviously, as you can imagine. Sometimes science fiction writers are better than, I don't know, physicists or scientists to predict the future, but we tried. So I will focus on hardware, algorithms, and applications. And if I start with hardware, we see already now the integration between quantum computers and HPC happening. We see hardware providers working together with the end users and software developers to co-design algorithms. And we see the first prototypes of so-called error-corrected, fault-tolerant quantum computers. This is a modality of quantum computers that will be free from errors because of construction, really. And this is already happening. When it comes to algorithm, we know that more powerful algorithms are nowadays available because they use so-called error mitigation. So they are able to remove, we are able to remove errors in post-processing and therefore enable more complex simulations. Hybrid solutions are happening. And of course, the synergetic combination of so-called error mitigation and error correction is also something that is very promising and will happen in these years. For applications, certainly we see applications in chemistry and material occurring already now. And I was mentioning these simulations from first principles of molecules that can be used as data set for AI. But also, we foresee the first inflection point that will correspond to really quantum advantage, and therefore to, if you want, something that will confer massive pricing power to the few first hardware and software vendors that will be able to offer these services. And for these, just as an example, in my startup, we are providing really a seamless interface between quantum processing units and HPC in what we call a digital quantum interface. In 10 years, hardware, so the platform that is more common nowadays is superconducting qubits platform, and we will see really many, many hundreds of thousands of qubits. So this means increasing complexity of the algorithms, and this will enable the development of applications of industrial relevance. Quantum computing market exceeding 50 billions, and obviously this will lead at the same time in breakthrough, including in high energy physics, where we will observe a simulation of, by quantum algorithms of subatomic particles, and therefore giving to scientists capabilities that nowadays are impossible. AI and quantum will be integrated in the drug discovery pipeline, and this will drastically reduce the cost and time to bring drugs to market. Applications, we will see a change or an adaptation of the algorithms from those that are developed for near term, so for the quantum computers that we have now, to those that will be typical of the error-corrected quantum computers. And of course, this will also lead to new applications that we cannot foresee yet, and therefore potentially new markets. And finally, 25 years, this is the most difficult timeline. Of course, via the cloud, we will have very powerful error-corrected quantum computers possessing millions of logical qubits, and therefore certain platforms, certain physical implementations will become obsolete, so that we will have like some winners in certain implementations of quantum computers. And for algorithms, one of the most important applications is in medical and pharmaceutical, but also financial institutions will start using quantum computer and leveraging quantum advantage. And this is the moment in which we believe the new market will unlock more than $2 trillion in economic value. And this will lead to disruptive change in healthcare and life sciences, where we will see impact in well-being and good health of really population worldwide, increasing even longevity. So maybe I will, perhaps, yes, perhaps. I will end, not end, but I will conclude with what is for me one of the most impactful applications. That is quantum computing combined with AI, because this will transform, really, in a way, medicine profoundly. In the drug discovery pipeline, we will be able to simulate in silico drugs in a very fast and cost-effective way. And it was almost very close to the end, but this is not working anymore. I promise you that I had another slide. And in this slide, I can anticipate, however, yes, this is almost the final slide. And the final slide goes back a little bit to the beginning about opposites and polarities. And I do believe that solving the most challenging problems that our society is facing really involves embracing differences. It involves thinking outside the box. And it involves really synergies and being really ready to work outside of our comfort zone. Because this is what it needed, but this is also what quantum physics and quantum computing is teaching us. I will leave you with this poem that I like very much. I will not read it, it's just for you, and I thank you for listening.
Thank you very much, Sabrina. Thank you for keeping the timing. We're doing really well. If you guys could put back the... Pouvez me dire combien de temps il nous reste? How much time you're giving us to finish, because we started a bit late. So we're going to take questions. Please raise your hands. We're going to start with this gentleman here, and then we're going to go here. Please introduce yourself briefly and ask a short question. Thank you.
Yes, hello. My name is Gabor Farkas. I'm with Geneva Macrolab. My question is, so with the deployment of AI and with the deployment of quantum computing, what kind of impact will quantum computing have? And can, I mean, we're already past we're going to fail the 2030 objectives set for the SDGs. Can we afford deployment of quantum computing and AI? Will they not have too big of an impact on the environment?
Absolutely. This is a very, very good question. And in a way, part of the answer, there are many ways, first of all, in which quantum can be combined with AI. In general, we talk about quantum for AI and AI for quantum, precisely because classical AI can help in developing quantum algorithms, and quantum algorithms can help in AI. In the example that I was presenting there, one of the ideas really is that if we are able to simulate ab initio, imagine if we were really able to have really error-corrected quantum computers, so we would be able to simulate molecules really ab initio in a powerful way. Then we wouldn't even need, let's say, or we would be diminishing the needs and requirements of AI. They would be precisely because we would have ab initio simulations. So in a way, there is a world really in which quantum computing will have impact in the resources, energetic resources available nowadays. And if we think in terms of the SDGs, obviously chemistry is at the basics, and I talked specifically about chemistry because this is what I know most, but it is at the basics of very many industries that can have an impact. For example, in climate, I think about fertilizers, I think about, in general, new ways of doing agriculture, I think about climate change. So having industries, all the industries that rely on chemical and materials will be tremendously affected by quantum computers. How? It's an interesting question. In which way we will combine it with AI? There are many proposals, but I think a lot of it will remain to be seen as the technologies mature and progress.
This is where you see the difference between a scientist who says, it's hard for me to make predictions beyond 5 years, and a business consultant says, oh, this market in 25 years, 2 billion. Sure. Yeah, big difference. Second question.
You were very positive in your speech. I might, well, ask you a question which is not so positive. We hear some experts in cybersecurity saying that with the power provided by quantum computing,
Yes.
it will be really easy to hack these passwords. And some believe you will need a totally new paradigm in order to defend, right, your computer, your environment. So can you comment on this, please?
Very good point. This is indeed what quantum computers are mostly famous for, a threat for national security, because they will be able to break cryptographic codes that are really at the basis of safety, if you want, of all nations. And indeed, there are a number of, actually, I have to say the truth, this is also what motivated if you want, competition and the rise of the quantum ecosystem. Precisely because of geopolitical issues and because of what was going on in China, in the US, we realized that, well, we have to, as much as possible, progress and understand, and all the countries have to have available quantum computers. Now, whether or not there will be actually a quantum computer that is able to break cryptographic code, it partly remains to be seen. I mean, of course, there are algorithms that are proven to be, in a way, to do exactly this. But I always say that, in theory, there is no difference between theory and practice, but in practice there is. So we don't have yet that level of that complexity of computers that would be enable this type of algorithms. And we will see, as the technology develops, whether or not they will be capable of doing so in practice. Not in theory, because in theory we know that they do, okay? But in practice. I have to add 2 observations. I hope I'm not... Yeah, I will just, a very quick observation. And this is that there exists already classical, so-called post-quantum cryptographic code that go beyond this that save the situation in a way, and the final and they are being adopted in all countries. And the final one is that it's important also to give positive use cases of quantum computers, because they exist and they can be disruptive. So I like to give positive applications, not just applications that could be, a threat for national security, which are there and we are taking care of them anyway.
Sabrina, do you have some bitcoins or some cryptocurrencies that would answer the question, that would show us how much you believe about current cryptographic solutions?
I can answer to this question.
Okay.
I don't. Can I say something more?
Please.
I was just, when I was having lunch the other day, I was saying that when bitcoins...
Satoshi Nakamoto, you know who he is? No?
When bitcoins, yeah, I know. When bitcoins first appeared, my dad, who is 84 years old, wanted to buy them, and me and my brother said, no, absolutely not. Now he would be, of course,
okay, so we stop listening to you about the future. Okay, don't ask her about the future.
Exactly. But it did happen. Just to, he's very angry still.
And after we go to you.
Yeah, thank you. I'm interested in how this feeds into, how do we close instead of growing the digital divide, and particularly what policymakers need to think about so that that divide doesn't grow, and also the gender digital divide. How can they leapfrog? Where do we go from here?
Yes, very, very interesting and important question. And I think that, I think the mission really of the Open Quantum Institute is really very much to democratize quantum and to make sure that not just few countries around the world that are the most wealthy countries possess quantum. And there are many ways of doing so. Again, I say Open Quantum Institute is doing a fantastic job for this, but also, for example, we are partnering with institutions like ICTP, the Institute of Theoretical Physics, which is a UNESCO institute that is really supporting many scientists from developing countries and giving them access to all the latest technology. So there are a lot of initiatives, and we have to make sure that this happens. And similarly, for the gender divide, I would say, well, okay, here I could talk very, very long, and I think that there there are many aspects. One of them is clearly mentorship. It is clearly having figures that really show with their example that there is no such thing like somehow that quantum physics or very highly technological fields are not inaccessible. I could talk too long. Maybe we will do this later on, but it's one of my passions actually.
Thank you. I'm Claudia, GESDA alumni. And I just wonder, I think the anticipatory briefing of quantum, it's very positive, and there's challenges, of course, but I do believe in the potential. But to get there, there's this AI and quantum require a lot of energy. So the energetic demand and the current crisis and forecasted one, how do you see the planification of both topics going together to advance and have positive applications?
Yes.
So Sabrina, just one thing to explain. So right now, AI, we hear that it's terrible for energy consumption, but with the current processors we have, which are GPUs from NVIDIA mostly, and the current algorithm, the question, I think there are two questions. One is like, do these algorithms need as much energy? Maybe not. And then I would like you to just precise it, because for me it's not clear. Is it going to be the same crazy consumption?
No. I mean, this is a very important point. It's related to this question, and there are actually specific initiatives aimed at quantifying and benchmarking energy consumptions for quantum computers nowadays. There are reports already available that are positive in what they believe. They say that I'm falling. Sorry. Okay. In what they say that actually, yes, that the quantum computers' energy consumption is definitely not at the level of supercomputers. But I would say that my opinion is that a lot remains to be investigated. So, I mean, there are really a number of instruments that have been created to study specifically this. I don't think that there is a final answer. The intuition is that it would be not at the level of
I mean, it's one of the hopes, right? Because typically when we go back to encryption, we hear that current algorithm would need years to break code, and quantum would be 5 seconds. So hopefully 5 seconds of quantum doesn't use as much energy as
I think
50 years
it is, but it is also a complex. What I can say also is that nowadays, I was telling you about this integration between quantum and AI. So many of the things that we do, we develop software, of course, and algorithms, we use HPC to enable quantum, but our algorithms are such that the better the quantum computers become, the least is the usage of the HPC. So obviously this means that, and quantum computers per se, exactly, so this means that this will reduce also the consumption in terms of supercomputers. But then again, I mean, it's a lot has to be investigated, and I don't have a final answer. I only know, and it's very good, that there are many initiatives specifically aimed at studying and understanding this, and the outlook looks positive.
Thank you. We'll end on a positive note then. Please give a warm round of applause to our speaker, Sabrina Maniscalco.
Thank you. Thanks.
And our next session is at 3. Come for Made in Space with Debbie Seneski. See you at 3 p.m. in the same room.